momentum and impulse. You've probably heard of momentum before. You may or may not have heard impulse. Probably you may be in a science fiction show or something like that. But we're going to talk about both, and they're definitely related. All right, momentum. Now, here's where in the year we start running out of variables to use. We have an M for mass. There's a capital M for something else we'll worry about later. So we're running out of M. So we use the letter P. Now, not a capital P because we already did that. That's power, right? We already got power. So this is momentum. Okay, lowercase p is momentum, right? And momentum is simply mass times the velocity of something. All right, and that makes sense because if you heard the word momentum before, you would know that if something is really big, it might have a lot of momentum, or if it's really fast, then it has a lot of momentum. And so you can see that momentum depends on something being very big and moving very fast. All right, so more momentum would be a big mass, right? Or really fast, a big velocity. No momentum. Can you have no mass? Well, yes. If you have no mass, you have no thing. There's nothing there, so that's silly. But you can have zero velocity. So I don't care how big your object is, right? If its velocity is zero, its momentum is zero, right? So you can have something huge, right? And it doesn't have momentum if it's not moving. All right. The units for momentum, right? So we have mass times velocity. And so that's kilograms is the mass. And velocity is meters per second. All right. Kilograms, meters per second. That's our units. And unfortunately, we don't have like a shorthand for it. It's just we're stuck with it. Kilogram meters per second. All right, we don't shorten it down. At least nobody does regularly. All right, is that a vector or a scalar? Well, is mass a vector? No, it's not a vector. Okay, is velocity a vector? Yes, it's velocity. Okay, so when I've talked about multiplying vectors by vectors, you can get a scalar. Well, this is just a scalar and a vector. So you're going to keep it as a vector. It's still going to be a vector. All right, so momentum is a vector. So you'll have momentum in a direction. You could have momentum up, momentum down, momentum left, momentum right. It's coming out of the page at you, whatever. All right. What measurement always has the same direction of momentum? Well, mass does not have momentum, but a direction, sorry, but velocity does. Velocity's direction is going to be the same as the momentum direction, right? That's what determines momentum. If you're going this way, that's the direction your momentum's going. All right, momentum. Boy, that is really hard to do in your own words. But to me, it is sort of like how hard it is to stop something thing. All right, that's really just kind of touchy-feely thing. But what's going on there, it's not how hard it is to slow down, right? Change its direction, to change its, right, to change its velocity. Well, that's the mass. That kind of determines how hard it is to change velocity. But if you have a mass and you multiply it by velocity, now you got some speed going. And your momentum is basically how hard it's going to be to make that go to zero, right? So if you have more mass, it's going to be harder to make it go to zero. If you have more velocity, harder to make it go to zero. That's kind of how I think about it. All right. So if the net force, ready, on an object, right, is equal to zero, then, right, if you have a force on something, you get a mass times acceleration. If you have a force and there's no force on something, you have mass and the acceleration then is zero. Okay, so that means you are not changing the velocity. The velocity stays the same, right, with zero force, zero velocity, zero acceleration, velocity stays the same. And so if velocity is the same, your momentum is constant, stays the same, right? If you have a net force, right, there's some sort of force going on, then you're going to have an acceleration, which means that the velocity is going to change and the momentum will change. Okay, so now again, a net force, that's like all of them together. If they all add up and cancel, then your momentum stays the same. If there's a net force, I mean you add up, you got some leftovers, then momentum will change. So you could think of a ball rolling along the ground, right? the forces up and down are equal, so it's just going to keep its velocity and it's going to keep its momentum. So there's forces, but they're equal. Whereas if you put a rock on the side of a hill, right, the forces aren't balanced anymore. There's up and down, the normal force and down, so they're not balanced. There's extra force pointing down, so the velocity is going to increase going down, and therefore the momentum, or momentum, is going to increase as well. All right, momentum and force. A little tricky, right? Force is going to change, right? That's going to change your acceleration, all right? And momentum is the describing. It's more like describing how the movement is going on. You need a force to change velocity. Force changes, actually technically changes velocity, but it's an acceleration. You need a force to change the velocity. And so if you change the velocity, you've got to change in momentum. All right. And so again, force is changing that velocity around. Momentum is measuring how much of that you got times the mass. Right. So having a momentum isn't going to affect or change something. Forces change things. Momentum just is. It's a thing that could get changed. All right. And it has to do with kind of how hard it is to stop something. If you get hit by something with a lot of momentum, you will feel it. Right. All right, then here is the deal. If momentum is mass times velocity, the units are kilograms and then meters per second. Check this out. What would happen if we went and said, okay, a force, which is kilograms meters per second squared. All right, that's a force. What if I multiplied that by time? That would multiply this by another second. They would cancel, and boom, shakalaka, you get kilogram meters per second, which is momentum. So let's try it again. What we're saying is force applied over a certain amount of time is going to give you the units of momentum. And so it is going to be the change in momentum. And that makes sense, right? If you push at something for a certain amount of time, it's going to change its velocity, which means its momentum is going to change. Okay, and this thing here is what we're going to call impulse. You can change something's momentum by pushing on it, but you have to push on it a certain amount of time. You can't just boom, push on it and not just like tap it. It's not going to change momentum. You have to push for a certain amount of time. And the longer you push, the bigger the momentum changes. So notice momentum is mass times velocity. Force times time is not momentum, it is the change in momentum. Okay? It's how momentum changes. Okay, the equation for impulse, right, is basically, we already said impulse is that change in momentum. And that equation is, therefore, the force times time. And if we wanted to be hardcore, we could say the sum of all forces times a change in time, right? We could be hardcore that way. The unit for impulse, right, based on that is still going to be Newton seconds, right? Newtons times time. But if you remember from 2 slides ago, that it's kilograms meters per second squared times a second, so it's just kilogram meters per second. That's the same units as for momentum.